Everything you are sitting on right now should have collapsed billions of years ago. The chair beneath you, the floor beneath that, the earth beneath that. None of it should exist. The atoms making up your body, the carbon in your bones, the oxygen filling your lungs with every breath, by every law of classical physics that scientists trusted for 200 years, every single one of those atoms should have spiraled inward, collapsed into a point, and annihilated itself in a fraction of a second. Not metaphorically, not approximately, literally. The atom, by classical physics, is a suicidal structure. It should destroy itself almost the instant it forms. And yet here you are, made of atoms, sitting on atoms, breathing atoms, alive because atoms stubbornly, impossibly, gloriously refuse to obey the laws they're supposed to obey. Here is the number that should unsettle you, by classical electromagnetic theory. A hydrogen atom, the simplest atom in existence, one proton and one electron, should collapse in approximately 100 picoseconds. That's 1/10 billionth of a second. In the time it takes you to blink, a classically well-behaved hydrogen atom would have collapsed and recollapsed about 5 billion times. Chemistry would be impossible. Matter would be impossible. You would be impossible. So why doesn't it collapse? The answer isn't simple, and anyone who gives you a simple answer is lying to you. The real answer requires you to abandon your deepest intuitions about what particles are, what motion means, what a location even is. The real answer reaches into a layer of reality so strange that even the physicists who discovered it spent their lives arguing about what it means. But the mechanism, the actual machinery of why atoms exist, is the most beautiful and disturbing thing in all of science. Let me show you how deep this goes. Start with something you can hold, a marble. You're holding it between two fingers, and you set it rolling in a bowl, one of those smooth ceramic bowls with gently curved sides. The marble rolls around the inside of the bowl in a circular path. Friction is slowing it down, very gradually, and as it slows, it spirals inward, circling closer and closer to the bottom until it eventually settles at the center. Energy dissipated. Motion ended. Marble at rest. Now here's the 19th century picture of the atom. Exactly this bowl in marble, but smaller. Much smaller. The proton at the center is the ball. Its positive electric charge creates an attractive field, curving inward toward the center like the bowl's walls. The electron is the marble, orbiting around the proton in a circular path, held in its orbit by electrostatic attraction rather than the bowl's geometry. This is the Rutherford model, named for Ernest Rutherford, who in 1909 fired alpha particles at a thin gold foil and discovered to his extraordinary surprise that atoms are mostly empty space with a tiny, dense nucleus at the center. Before that experiment, physicists imagined atoms as diffuse puddings of charge, electrons embedded throughout like raisins in a bun. Rutherford's gold foil experiment blew that apart. Atoms have nuclei. Electrons orbit around them, the marble in the bowl. The problem arrived almost immediately, and it arrived from Maxwell's equations, the four elegant equations James Clerk Maxwell derived in 1865 that describe everything about electricity and magnetism. Maxwell's equations are not wrong. They are spectacularly, extraordinarily right. They predicted radio waves before anyone had detected them. They correctly describe every electrical and magnetic phenomenon we've ever measured, from the magnetism of a refrigerator door to the propagation of light across intergalactic space. And Maxwell's equations say, with perfect mathematical certainty, that an accelerating electric charge radiates energy. Always. No exceptions. Now, an electron orbiting a proton is accelerating. This is not a philosophical statement. This is physics. Circular motion requires centripetal acceleration, the constant inward pull that keeps the orbiting object from flying off in a straight line. The electron, as it orbits, is continuously changing direction, which means it's continuously accelerating, which means, by Maxwell's equations, it must continuously radiate electromagnetic energy. Light, in other words, and that radiated energy must come from somewhere. It comes from the electron's orbital energy. As the electron radiates, it loses energy. As it loses energy, its orbit shrinks. As its orbit shrinks, it orbits faster, which makes it radiate more, which makes it lose energy faster, which makes the orbit shrink faster. A death spiral, an accelerating collapse. The calculation is clean and ruthless. The electron should spiral into the proton in about 100 picoseconds, releasing a characteristic burst of radiation as it goes. Every atom in the universe, gone. Just like that. So why doesn't it happen? Why do atoms exist at all? The first person to try patching this was Niels Bohr in 1913. Bohr was a young Danish physicist working in Rutherford's lab in Manchester, and he did something that, by any rigorous scientific standard, should have been embarrassing. He simply declared that electrons can only orbit at certain fixed distances from the nucleus, specific, discrete, allowed radii, and that while they're in those orbits, they don't radiate. They just don't, despite Maxwell's equations saying they should. Bohr didn't explain why. He couldn't explain why. He just postulated it and showed that his model correctly predicted the wavelengths of light emitted by hydrogen atoms, which matched experimental measurements with astonishing precision. It was a calculated act of intellectual desperation. Bohr knew his model was wrong at a foundational level. It had no mechanism. It had no explanation. It was a mathematical patch on a broken theory, and it worked far better than it had any right to. The predicted spectral lines for hydrogen, the specific colors of light emitted when hydrogen atoms are excited, meshed observation to 4 decimal places. Something real was in there. Something the patch was accidentally touching. But what? The answer came in 1924 from a French physics doctoral student named Louis de Broglie, and it came in the form of a question so simple and so outrageous that his thesis committee wasn't sure whether to pass him or have him evaluated. De Broglie asked, if light, which we know to be a wave, can behave like a particle, as Einstein showed in 1905, then why can't a particle, which we know to be a particle, behave like a wave? He did the mathematics. He showed that every particle, every electron, every proton, every object, has a wavelength associated with it. The de Broglie wavelength, as it's now called, is equal to Planck's constant divided by the particle's momentum. For a baseball moving at 100 miles per hour, the wavelength is absurdly small, about 10 to the power of negative 34 meters, far smaller than any nucleus, completely undetectable. For an electron orbiting a proton, the wavelength is comparable to the size of the atom itself, about 1/10 of a nanometer, 10 to the power of negative 10 meters. Not small at all on atomic scales. And here's where the marble analogy finally breaks. The electron isn't a marble orbiting in a bowl. It's a wave. Specifically, it's a standing wave, like the wave on a guitar string that vibrates in fixed patterns. A guitar string can only support certain wavelengths, those where a whole number of half wavelengths fits between the fixed endpoints. Other wavelengths cause destructive interference. The vibrations cancel themselves out. Only the resonant patterns persist. Bohr's fixed orbits are exactly the orbits where a whole number of electron wavelengths fit around the circular path. Not 2.5 wavelengths, not 3.7. Exactly 1 or 2 or 3 or any whole number. Those are the only stable configurations. Everything else self-destructs through interference. The electron can only exist stably where its wave nature allows it to form a closed, self-reinforcing loop. This is not metaphor. This is the mechanism. Electrons don't collapse into the nucleus because wave patterns don't collapse to points. A standing wave on a guitar string doesn't collapse to a single location along the string. It exists as an extended pattern over the whole string, with regions of high and low amplitude. The electron, as a wave, cannot be localized to a point, and the nucleus is, by atomic standards, a very tiny point. But wait, this explanation, elegant as it is, still doesn't go deep enough. It explains why certain orbits are stable. It doesn't explain why the electron doesn't just stop and sit at the lowest energy state, touching the nucleus. Waves can have zero amplitude after all. Why can't the electron wave just collapse to 0 to nothing, sitting perfectly still at the proton's location? This is where we need Heisenberg. Werner Heisenberg in 1927 was 25 years old when he derived the uncertainty principle, one of the most misunderstood results in all of science. Popular accounts treat it as a measurement problem. You disturb the electron when you try to observe it, so you can't know its position and momentum simultaneously. This is wrong. It's not a measurement limitation, it's a statement about reality itself. The Heisenberg uncertainty principle says that position and momentum are not independently defined quantities. They're complementary variables in the mathematical structure of quantum mechanics related by the Fourier transform, and they cannot both have precise values simultaneously for any quantum system, regardless of whether anyone is measuring or not. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4 pi. Always, everywhere, for everything. Think of it like this. Imagine you're trying to describe a wave. A water wave, say, with perfect precision. You want to know exactly where the wave is and exactly what its wavelength is. But these are incompatible requirements. A wave with a perfectly defined wavelength must extend infinitely in all directions. It's a pure sine wave going on forever. That's a wave with perfectly defined momentum but completely undefined position. To localize the wave to a specific region, to make a wave packet that exists in a small region of space, you have to add together many different wavelengths, superimposing them so they interfere constructively in a small region and destructively everywhere else. But now you have many wavelengths, which means uncertain momentum. Position certainty costs momentum certainty, and vice versa. This is not engineering, this is mathematics. This is the structure of what waves are, and since electrons are waves, it applies to them absolutely. Now apply this to the collapsing atom. Suppose the electron actually did collapse into the nucleus. Its position would become extremely well defined. It would be at the proton's location, within a radius of about 1 femtometer, 10 to the power of minus 15 meters. By the uncertainty principle, a position uncertainty that's small requires a momentum uncertainty that is enormous. Specifically, the momentum uncertainty would be on the order of Planck's constant divided by the nuclear radius, a calculation that gives a momentum corresponding to kinetic energy of hundreds of millions of electron volts, which is the energy scale of nuclear physics, not atomic physics. An electron with that much kinetic energy doesn't sit in the nucleus, it blasts out of it instantly, escaping the electrical attraction of the proton with energy to spare. The very act of being localized gives the electron the kinetic energy to delocalize itself. Confinement creates momentum. Momentum creates momentum. Momentum creates motion. Motion prevents confinement. The atom reaches equilibrium not where the electron sits at the nucleus, but where the energy cost of confinement, the uncertainty principle mandated kinetic energy, is balanced against the energy benefit of being close to the proton. This equilibrium occurs at a specific distance, the Bohr radius, approximately 0.529 angstroms or about 53 picometers. Not because Bohr declared it, but because quantum mechanics mandates it through the physics of waves and uncertainty. The atom doesn't collapse because collapse is energetically forbidden by the wave nature of matter itself. Let me zoom out from a single hydrogen atom to the universe. Because this mechanism, this remarkable prevention of collapse, operates at every scale, and its consequences are written across the entire cosmos. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, says that no two electrons can occupy the same quantum state simultaneously. This is a direct consequence of the fermionic nature of electrons, their quantum statistics, and it has nothing to do with forces or interactions. It's a pure symmetry constraint on how indistinguishable particles can arrange themselves. Think of it as the universe's version of the rule that no two things can occupy the same seat at the same time, except applied to quantum states rather than physical seats, and enforced by the mathematics of probability amplitudes rather than the physics of solid matter. This principle is why matter has volume. Without it, every electron in every atom would collapse down to the lowest energy state. All the electrons in carbon, 6 of them, would pile into the 1's orbital, the lowest rung. The atoms would be tiny, identical, with no chemical complexity. Chemistry as we know it would vanish. The periodic table would have one entry, not 118. Life would be impossible. Because of Pauli's principle, electrons fill higher and higher energy levels as you add more of them to an atom. Carbon's 6 electrons fill the 1's 2's and 2p orbitals, giving it 4 valence electrons available for bonding. It's the structure, this forced occupation of higher energy levels mandated by quantum statistics, that makes carbon the foundation of organic chemistry and, therefore, of life. Now scale up further. Take a white dwarf star, the dense remnant left behind when a star like our Sun exhausts its nuclear fuel and sheds its outer layers. A white dwarf contains roughly the mass of the Sun compressed into a volume the size of Earth. Its density is about 1 million times that of water. A teaspoon of white dwarf material would weigh about 15 tons. What's holding it up? Not nuclear reactions. Those have stopped. Not thermal pressure. The star is slowly cooling. What prevents the electrons in the white dwarf from being compressed further under the immense gravitational pressure of a solar mass worth of material? Degeneracy pressure. Electron degeneracy pressure, to be precise. The Pauli exclusion principle, operating at stellar scale. The electrons cannot all collapse to the same quantum state. To compress them further would force them into higher and higher momentum states, by the uncertainty principle requiring more and more energy. The electrons push back against compression not through temperature and nuclear burning but through pure quantum mechanical stubbornness. The same mechanism preventing a hydrogen atom from collapsing operates at the scale of a stellar remnant, holding up a 1,000,000-kilometer ball of dense plasma against the gravity of an entire sun. Imagine that scale. The same mathematics that keeps the electron in your carbon atom from spiraling into the nucleus keeps a white dwarf star from collapsing into a black hole. The same principle, the same numbers. The universe uses the same rule at the scale of picometers and the scale of planetary radii. But even degeneracy pressure has limits. Add too much mass to a white dwarf, above about 1.4 solar masses, the Chandrasekhar limit, first calculated by the Indian physicist Subrahmanyan Chandrasekhar in 1930 at the age of 19 while sailing from India to England, and the electrons are pushed to relativistic speeds. Relativistic electrons have different energy-momentum relationships, and their degeneracy pressure cannot keep up with gravity. The white dwarf collapses. If it becomes a neutron star, neutron degeneracy pressure takes over. If enough mass accumulates, even that fails, and a black hole forms. The existence of matter, the existence of stars, the existence of black holes, all of it is a story about whether quantum mechanical resistance to collapse can overcome gravitational attraction. And quantum mechanical resistance to collapse begins with the atom that shouldn't exist. Now let me show you something that should genuinely disturb you. Not in a frightening way, but in the way that all genuine understanding of nature disturbs. By removing a floor you didn't know you were standing on. The atom that shouldn't exist is also the atom that isn't quite there. The electron in a hydrogen atom isn't actually orbiting the nucleus in any classical sense. It doesn't have a definite position. It doesn't trace a path. It doesn't occupy a specific location between measurements. It is described by a wave function, a mathematical function extending throughout all of space, though concentrated most densely around the nucleus, that represents not where the electron is, but where it is likely to be found if someone looks. The electron exists as a probability cloud, not a cloud of ignorance where the electron is really somewhere specific and we just don't know where. A cloud of genuine indeterminacy, where the question, where is the electron right now, has no answer. Not because we lack information, but because the question itself is malformed for quantum objects. Suppose you could somehow photograph the hydrogen atom 1,000 times, each time measuring the precise position of the electron. You'd get 1,000 different answers, scattered throughout a region roughly an angstrom across. Plot them all, and you'd see a density pattern. Higher density near the Bohr radius, lower density close to the nucleus, and far from it. That matches the square of the wave function. The Born rule, proposed by Max Born in 1926, says that the probability of finding the electron at any location is proportional to the square of the wave function's amplitude at that location. But between measurements, the electron doesn't exist at a specific location. It exists as a superposition of all possible locations weighted by the wave function. It's everywhere in the cloud and nowhere in particular. This should bother you. It bothered Einstein enormously. He spent the last 30 years of his life convinced that quantum mechanics was incomplete, that there had to be hidden variables, some underlying reality where the electron really did have a definite position, just one we couldn't access. He and Bohr argued about this at conferences throughout the 1920s and 1930s in debates that became legendary in the history of science. Einstein's position was summarized in his famous line, "God does not play dice." Bohr's response was equally famous. Einstein stopped telling God what to do. John Bell, in 1964, devised a mathematical test, Bell's theorem, that could distinguish between quantum mechanics and any hidden variable theory. Subsequent experiments, most definitively by Alan Aspect and his team in 1982 and refined numerous times since, showed definitively that quantum mechanics is correct and hidden variable theories are wrong. The electron genuinely does not have a definite position between measurements. Einstein lost. Reality is not what he, or any of us, intuitively expected. The atom exists because the electron doesn't have a position. The stability of matter rests on the fundamental indeterminacy of the quantum world. Let me make this concrete with a thought experiment. Imagine you could shrink yourself to the size of an electron, about 3 orders of magnitude smaller than a proton. Though size of an electron is a concept that requires serious qualification, and you're inside a hydrogen atom trying to observe the electron. You wait. You look around. The proton is at the center. A dense little nugget of positive charge, enormous compared to you at this scale, radiating its electric field in all directions. Where's the electron? You can't see it anywhere in particular. You detect its influence. The electric field is modified by its presence in a diffuse, spread-out way. But there's no electron object hovering in orbit, no marble tracing a circular path, no BB rolling around the inside of a bowl. You decide to measure it. You bounce a photon off it to determine its location. You get a result. The electron is at a particular position, roughly half an angstrom from the proton. Good, you measured it. But the instant after your measurement, the wave function collapses. The probability cloud collapses to the measured location, and then immediately begins to spread out again as quantum mechanical time evolution takes over. A nanosecond later, the electron is spread through the entire probability cloud once more. Now try to measure it again. You get a different answer. You measure it 1,000 times. Each time, you get a position drawn from the probability distribution described by the wave function. No two measurements are identical. The electron is not at any particular place. It simply has a propensity to be found at various places described by the wave function. Now here's the disturbing part. This isn't a feature of electrons specifically. This is a feature of everything. Everything obeys quantum mechanics. Your coffee cup obeys quantum mechanics. The chair beneath you obeys quantum mechanics. Their wave functions are so fantastically narrow, because of their enormous mass compared to an electron, that the spread of positions they could be found in is smaller than a proton's radius. For all practical purposes, they have definite positions, but in principle, in the deep mathematical structure of reality, they are spread out probability clouds, just like electrons, just with clouds so narrow as to be effectively points. You live in a quantum universe. You are made of quantum objects. The solidity you feel, the apparent definiteness of everyday reality, is a statistical effect of enormously many quantum objects averaging out into classical behavior. It's not the fundamental nature of things. The fundamental nature of things is the hydrogen atom's electron cloud, extended, indeterminate, existing as potential rather than actuality, until measurement forces a choice. Erwin Schrödinger, who gave us the wave equation governing how quantum states evolve through time, was simultaneously the person who found the implications most troubling. In 1935, he wrote a paper presenting a thought experiment designed to expose what he considered an absurdity in quantum mechanics. He imagined the cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers a mechanism that breaks the vial and kills the cat. Quantum mechanics says that before measurement, the atom is in a superposition of decayed and not decayed states. If you take quantum mechanics literally, Schrödinger argued, the cat before you open the box is in a superposition of alive and dead states. He intended this as a reductio ad absurdum, proof by showing ridiculous consequences against taking quantum mechanics literally at macroscopic scales. But Schrödinger's cat became, ironically, the most famous illustration of quantum superposition in history. The thought experiment backfired. Instead of exposing an absurdity, it illuminated the genuine strangeness of the quantum world, and the profound difficulty of explaining where quantum behavior ends and classical behavior begins. The answer is that quantum behavior never ends. The cat genuinely is in a superposition, in the full mathematical sense, before you open the box. The reason it doesn't seem that way is decoherence, the process by which quantum superpositions become entangled with environmental degrees of freedom and lose their coherent interference, behaving statistically like classical mixed states. But decoherence is not collapse. It doesn't eliminate the superposition. It makes it effectively invisible, spread across the correlations between the cat and the 10 to the 23rd molecules of air in the box and the walls and the detector. The atom that shouldn't exist doesn't collapse because of quantum mechanics. The quantum weirdness that prevents atomic collapse is the same quantum weirdness that makes Schrödinger's cat confusing. These are not separate mysteries. They are the same mystery viewed from different angles. Let me now bring this all the way home to you, personally, because this is where it stops being physics and becomes something closer to philosophy. And in the best tradition of Feynman, I refuse to shy away from that. You are reading this with eyes made of atoms that shouldn't exist. Your brain, processing these words, consists of roughly 100 billion neurons, each containing on the order of 100 trillion atoms. Each atom stable because quantum mechanics prevents its electrons from doing what classical physics demands they do. Every thought you have, every memory you access, every emotion you feel, all of it runs on quantum mechanical stability. Without the atom that shouldn't exist, there is no brain. Without the brain, there is no thought. Without thought, there is no science. Without science, there is no understanding of why atoms shouldn't exist. The universe has produced through quantum mechanical luck or necessity the very structures capable of understanding the quantum mechanics that produced them. We are the universe's way of knowing itself at atomic scales. And what we discovered is that the level of reality on which we stand, atoms, molecules, chemistry, biology, rests on a foundation that violates classical common sense at every point. The electron in every carbon atom in your body has no definite position. Right now, it exists as a probability cloud around a nucleus, a smeared quantum potential, not quite here or there, prevented from collapsing into the nucleus by the Heisenberg uncertainty principle, prevented from abandoning the atom by the electrostatic attraction of the proton, existing in a delicate quantum equilibrium that has persisted, for the carbon in your body, since those atoms were forged in the interior of dying stars between 5 and 7 billion years ago. You are the downstream consequence of quantum mechanical accident reaching back 7 billion years. Every atom in you was made in stellar nucleosynthesis. Every atom survived because quantum mechanics prevented collapse. Every chemical bond holding your molecules together is a quantum mechanical phenomenon. The covalent bond, the shared electron pair, exists only because electrons are waves that can span two nuclei simultaneously, creating the region of constructive interference between them that lowers the overall energy of the system. Nothing in you is classical. Nothing in you obeys Newton's laws at the atomic level. And yet here you are, apparently solid, apparently definite, apparently located at a specific place and time, thinking specific thoughts. The classical world you experience is a macroscopic average of a quantum indeterminacy. You are the statistical shadow of a quantum reality. So the next time you pick up a rock, a piece of granite, say, cold and solid and absolutely unambiguous in its rockiness, hold it for a moment and think about what you're actually holding. Not a collection of tiny billiard balls orbiting each other. Not a classical system of charged particles following deterministic trajectories. You're holding a collection of quantum probability clouds, electron wave functions overlapping and interfering and exchanging information through photons, all of it settling into a macroscopic average that your nervous system, itself a collection of quantum probability clouds, interprets as solid, as cold, as gray, as real. The rock exists because the atoms that shouldn't exist do exist. They exist because electrons are waves, because waves cannot be confined to points without explosive momentum, because the uncertainty principle is not a limitation on measurement but a statement about the structure of reality, because Pauli's exclusion principle prevents matter from collapsing into identical lowest energy configurations and gives the periodic table its richness in chemistry, its complexity in biology, its possibility. The atom that shouldn't exist is the most important object in science, not because it's strange, but because its strangeness is the price of everything. Quantum indeterminacy isn't a bug in the universe's code. It's the feature that makes the universe capable of containing anything at all. Without it, the collapse happens. In 100 picoseconds, all the matter in the universe, all the hydrogen in the early universe implodes. No stars, no galaxies, no planets, no chemistry, no life, no one to wonder why. The universe is stranger than classical physics promised, but it is also, because of that strangeness, vastly more rich, vastly more durable, vastly more capable of producing complexity than any classical universe could ever be. The uncertainty that seems to undermine solidity is exactly what provides it. The indeterminacy that seems to threaten reality is exactly what enables it. We exist in a space that quantum mechanics carved out against the demands of classical electrodynamics. We are the children of the atom that shouldn't exist.